Hello, beginning Physics 112. Fortunately, I know many of you, but some of you I haven't met yet. So anyway, let's get started and get you ready for assignment 1. But first of all, a few preliminary issues. So let's review Physics 1. So pause the video for a second, look over this list, and see if you recognize everything on here. Okay, so significant figures, scientific notation, and units, those will remain important. I'll keep reminding you. So I'm not going to review those rules, but if you need help with that, come to see me, go to one of the tutors, talk about it in your study groups. Kinematics is motion, so if you read that, you should say, oh yes, I remember that. That's displacement, velocity, and acceleration. We have all those equations. You should keep your equation sheet from Physics 1. In fact, I should probably post it on our website in case you have lost it. Scalars and vectors, this will be incredibly important this semester. And so how to add vectors, vector components, all that trig. If you've forgotten it, it's going to come up in week 1 and in assignment 1. Newton's 3 laws of motion, I'm not going to review them, but the most used of all the 3 is the second law, F equals ma. Energy and energy conservation, work, kinetic energy, potential energy, remember all that? You're going to have to remember it. Momentum, P equals mv, conservation of momentum, an isolated system, right? In an isolated system, momentum is conserved. We know all that. That will come up a lot this semester as well. And that's our conservation laws, conservation of energy, conservation of momentum. And this one we didn't study actually. That's conservation of angular momentum. And finally, we did gravitation. And we learned about vectors and scalars and fields. And in week 2, we're going to go in a big way into that area. Okay. Okay, here we go. Week 1. Oops. Electrostatics Introduction. So the textbook supports this material. I think it's chapter 5. These are the pages. The pages, there's the textbook pages, and then the textbook is a PDF document. It has slightly different page indications, so I give you both of them. You might look that over if that helps you. Keep in mind also that you have lots of other online resources. So watch this video, and if you find other resources that you think are good, you can share those with me and your fellow students. So first of all, we'll talk about electric charge, its nature and its origin. We'll talk about the properties of electric charge. You need to know these 2 important properties of electric charge. It's quantized and conserved. I'll talk about that. How objects are charged, the term electron affinity and electronegativity, conductors and insulators, polarization, Coulomb's law, and the superposition rule. Those are the things I'm going to cover in this lecture. If you're coming back for a second time, you can jump around. That's the advantage to this. So if there's some area of here that you need to review, you don't have to watch the whole video. But for most of you, I think it's a good idea to watch the whole video from beginning to end at least once. Okay, a little review of chemistry and nuclear physics, understanding the structure of matter. Most of you, I hope all of you actually, this is just a review, but let's talk about it. You know about the periodic table, 92 naturally occurring elements and several man-made elements. And each element has an atom of a different structure. So matter is made of atoms, and atoms combine molecules to make compounds. All this should be familiar to you. And if we go to the periodic table and step through the elements, what we see is the first element is hydrogen. And all the atoms are made of three particles: protons, neutrons, and electrons. The protons and neutrons are in the nucleus, and the electrons are in a cloud or shell or orbitals, different ways of thinking about it, around the outside of the atom. Atoms drawn here are not to scale, so if the nucleus of the atom were this big, the electron would fill a volume that's probably 50 to 100 meters in diameter. In other words, the nucleus is tiny, the electron cloud is huge. An analogy is often our solar system, where most of the matter of the sun is in the sun at the center, and the planets just having a little bit of mass are spread out all over the place. Okay, so that's our review. So one proton is hydrogen, two protons are helium, and then it goes 3, 4, 5, 6 protons would be carbon. So hydrogen normally doesn't have a neutron. Helium in its most common form has 2 neutrons and 2 protons, and so has 2 electrons. And carbon, which has 6 protons and 6 neutrons, so 12 particles in the nucleus, and has 6 electrons. And so these are neutral atoms. If you remove an electron from an atom, it's a charged atom, and it's called an ion. And so the fundamental unit of charge in nature is the electron and the proton. And so that's our fundamental unit of charge. We'll discuss that more later. And this is the basis on which we say charge is quantized. You can't cut an electron in half. You can't cut a proton in half and get 2 half charges. In fact, we won't discuss this too much here, but if you cut a proton, it splits into 3 quarks. So there is some structure beyond the proton. But for our purposes, the fundamental units of charge are the proton and the electron. And entering the realm of nuclear physics, we will briefly discuss that if you put a proton and electron together, they become a neutron. Or in some nuclear reactions, a neutron can split into a proton and electron. Okay, so that's the structure of matter. It's important to know that. That's a good model to have, to be familiar with. What is important for us this week is that the electrons are on the outside of the atom and fill the volume of the atom. And so when an atom gets changed or affected or reacts with other atoms, it gains or loses electrons. And that's how we get charged objects. So an atom is usually neutral, but if we ionize it, if we cause it to lose an electron or gain an electron, it can become charged positively or negatively. So, once again, excluding quarks, the electron is the smallest unit in nature of negative charge. We give it a charge unit of E. That's the charge on the electron. This little e doesn't mean electron. It's a symbol for electronic charge. It's the symbol for that fundamental unit of charge in nature. You will see that in general, in the metric system, in the international system of units, the coulomb is the measure of charge. And so we need a conversion factor between 1.6 times 10 to the minus 19 coulombs is the value of 1 electronic charge. So This, of course, existed before we knew about this, and that's why this unit still is widely used, but we need to be able to convert. So the proton has a charge exactly equal to the electron, and that's the unit of one electronic charge, and it's positive, and so it's positive 1.6 times 10 to the minus 19 coulomb. This is all on your equation sheet. So this idea, this recognition, is the quantization of charge. So when we say charge is quantized, we mean that, let me pause the video. So you're asked to explain in words by writing what quantization of charge means. It means that charge in nature comes in smallest discrete fundamental units. Those are the key words to describe the quantization of charge. And those units are the electron and the proton, and the value of charge that they have in coulombs is 1.6 times 10 to the minus 19 coulombs. That statement that I just made is a description of the quantization of electric charge. The fact that electric charge is conserved, remember conservation of energy, we used to say energy can't be created or destroyed, it just transforms from one form to another, right? Like kinetic energy becomes potential, or you drop a ball and potential energy becomes kinetic. That concept is very important, the conservation concept. And in the case of electric charge, the statement should not be that charge can't be created or destroyed, because in fact it can. So the statement should read, let me write it on, let me pause and write it out. Okay, here's the statement for conservation of electric charge. The total net charge, of a closed system is constant. And so if you say charge can't be created or destroyed, that's generally true, but there is an exception to that. In nuclear reactions, a proton and an electron sometimes combine to form a neutron. So we destroyed two charges and got a neutral charge. Conversely, in some nuclear reactions, a neutron can split into a proton and electron and charge is created. So the stronger and truly correct statement is that in a closed system, the total or net charge of that system will remain constant. That's what we mean by conservation of charge as opposed to quantization of charge. Okay, I'm trying to keep this video from being too long. So I urge you to pause the video now and read through this diagram. There's 3 columns and 3 situations. Just pause the video and read through it. That way, when I talk through it, I can go a little bit faster and you'll know what I'm talking about. So do that. Okay, let's walk through these 3 situations. The first one is we have 2 plastic rods. If we hang one up, this is actually what we would do in lab if we had a real lab. But unfortunately, because of COVID, you won't be able to get to do this in the real lab. So this is important. You take a plastic rod, you hang it up so it's free to move, you bring another plastic rod next to it, there's no response. If you take the 2 plastic rods and rub them on fur, both rods, since you're doing the same thing, will become negative and the hung rod will be repelled by the other rod. So just, it's not here explained, but what's happening is electrons are being transferred. So the rod has more, notice the words, electron affinity or electronegativity than the fur. So the rod tends to pull electrons off the fur making the rods negative and not shown here, the fur becomes positive. Why? Because of conservation of charge. So any charge that goes from the fur to the rod will make the rod one charge more negative and make the fur one charge more positive. If you take glass and rub it on silk, which is another thing we would do, notice, of course, if the glass rods are uncharged, they have no influence. Once we rub them on the silk, both rods become positive, and they do the same thing. So like charges repel. If you take the negative plastic rod and the positive glass rod and you hang them next to each other, they will attract. So opposites attract, likes repel. And here it shows you that the fur, since the electrons transferred from the rod to the fur is positive, and so it will attract that rod. And the wool became negative because the wool, I didn't explain that, the wool is more electronegative than the glass, or the wool, notice the term, has more electron affinity than the glass, and so the wool takes electrons off the glass onto the wool, leaving the glass positive. Okay, so this is an activity that we do in lab, and it's going to be restricted now to seeing it on the screen. But those are all important concepts. And if we then, move this out of the way, go back to our list, we see the terms charging objects. We discussed electron affinity and electronegativity. Okay, now we're ready to talk about conductors and insulators. Before we do that, let me just, I have this one diagram, so let me show you just what we were talking about. Here's a piece of fur, here's a piece of plastic, and we see the electrons going from the fur to the plastic. Actually, it's not a very good diagram, because if there's 4 plus 3 negative charges that have left the fur, what we should see is 7 positive charges left on the fur, meaning positive because it's a lack of electrons. Notice, just a reminder if you haven't noticed, protons don't transfer because they're in the nucleus. It's always the electrons that transfer. So things become positive by losing electrons, things become negative by gaining electrons. Just to add an example that comes from chemistry. Hopefully you've had chemistry. Sodium as a neutral atom tends to lose an electron to chlorine as a neutral atom because of their electronic structure. So if you've studied this in chemistry, sodium has one outer electron that's easily removed, and chlorine has a strong affinity for electrons. And so chlorine, under certain chemical conditions, will pull an electron off of the sodium, leaving the sodium positive and the chlorine negative, and then they bond together by this electrostatic attraction, which in chemistry is called an ionic bond. So this part is pretty straightforward. Conductors are material that conduct electricity, allow electrons, those are the charges that move, to move through them, and insulators are materials that prevent the flow of electrons, which later we'll call current. So the key phrase, you want to remember this phrase, is free electrons. Conductors have free electrons. So if you take a conductor like copper, inside the copper are electrons that are not attached to the individual copper atoms, and they're free to move through the copper. Something like glass, which is an insulator, has no such free electrons. For completion, we could name semiconductors, which have a limited conductivity. They're important in modern electronics. And then there are also superconductors, where the electrons move so freely that there's no resistance to their motion. But for this week, all you need to know is conductors and insulators. Examples of conductors. Of these, silver is the best conductor, copper is next. Aluminum, which is not on here, is also a good conductor. And if we were having lab, you would see we use aluminum a lot as a conductor. Gold, actually, I'm not sure about gold. It may be a better conductor than silver. That I don't know. Steel is not a great conductor. Seawater is not a great conductor, but they are conductors, especially because of the salt, right? Those are ions, charged particles in the water. It makes it a better conductor. Rubber, glass, most forms of oil, diamond, wood, and another common insulator is plastic, which is also not on here. So those are just examples of conductors and insulators that you're familiar with. Okay, imagine what you're looking at is a aluminum sphere that's neutral. So it's aluminum, it has free electrons, it has everything is charges in it, but when it's neutral, it just means the charges are balanced and cancel. So the net charge is 0. And so we have this aluminum sphere sitting here, and we bring in and put next to it, let's say, a negatively charged rod that we rubbed on the plastic on the fur. So what happens? Pause the video and think about if you know what happens. Okay, this is what happens. See if you get it right, what happened correct, and the reasons correct. So this rod, the free electrons in the rod, since they're free to move as far away, they're being repelled by the rod, so the free electrons in the rod move as far away as they can get. They move to the far side of the aluminum sphere. Actually, in lab, we do this with a soda can, which is made out of aluminum. And on its side, we can actually do this, and the electrons go over here, and that leaves the positive, a net positive charge on the front side. So that's exactly what happens if you said, oh, the positive charges move toward the rod because they're attracted, and then that's generally correct, but in fact what happens is the electrons are free to move. Free electrons move to the far side, leaving a net positive charge on the near side. And what does that mean? Well, that means that this side of the can is attracted to the rod, and the far side is repelled. But when we do this in class or in lab, you'll see the can attracts, or the sphere attracts to the rod. And the reason is this side of the can is further away, and so the force of repulsion on the far side is weaker than the force of attraction on the near side. And if we were to change the rod so that it were positively charged, we take the glass rod so it's positively charged, what would the difference be? Pause the video and explain to yourself. Hopefully you got it right. Now the free electrons attract toward the rod, so they come to the near side. The positive charges are left behind, unbalanced positive charges. That's even a better way of saying it, because they're all mixed. Right now we have electrons over here, that leaves positive charges over here. The force of attraction of the near side to the rod is stronger than the force of repulsion of the far side with the rod, and so the net effect is the same. So if we did this in lab, which we usually do, is we take a neutral can, we lay it on the table, soda can, we charge a rod negatively, it attracts it. We charge a rod positively, it also attracts it. This is an example of polarization. Separation, a neutral object remains neutral. Notice this is still neutral, conservation of charge, but the charge is not evenly distributed and the can has an electrical polarity. It has a positive side and a negative side. Okay, 5 different situations, A through E. Consider each of these cases isolated from each other. They're not next to each other, they're far apart. These are all point charges, so they're small little spherical charges. And we have 2 equal positive charges next to each other. 2 equal negative charges next to each other. A positive and a negative, a positive and 4 positives, and a positive and 4 negatives. Let me make one adjustment to this. So imagine in each of the 5 cases we start out with 2 neutral balls hung from strings from some rod or fixture, and then we put the charge on them. So what's going to happen to those 2 if they're both positive, both negative, blah blah blah, all 5 situations on these 2 balls? What's going to happen? Predict that. Go through it. I mean, really go through it. Don't just listen to the video. Try and interact and make your predictions for all 5 situations and then come back. Oops, I should have mentioned, draw vector arrows. So in the case of this one, they're going to repel, and the force is going to be equal and opposite. And if the 2 balls were hanging, they would separate equally like this. And the angle of separation, how much they pushed apart, would be proportional to how strong that force would be, right? So the angle is going to be proportional to the force strength. Okay, so now repeat this situation for the other 4 cases, and then come back. Okay, I'm going to step through all 4 cases. So we did case 1. Case 2 is going to be the same thing, only these will be negative, right? They're going to repel each other equal and opposite, and they'll swing out to a certain angle depending on the force strength. In this case, the force is going to be attractive, and if they're far enough apart that they don't touch, they'll swing toward each other until they're in equilibrium. Remember, the force that's keeping them from going further is there is a force of gravity. We'll talk about that later. So, surprisingly enough, when you get to D, I won't be surprised if you got this wrong, this, when you quadruple the force of this charge, this force vector should be 4 times longer than this vector. I didn't really draw it to scale, but because there's 4 times as much charge here, the force is going to be 4 times stronger, but it's 4 times stronger in each direction. So this you might have guessed wrong. This is Newton's 3rd law. If the force increases 4 times, then charge A is pushed, the first charge pushes on the second charge, and the second charge pushes on the third charge, and that has to be equal and opposite. We'll see that in a minute. And in the case of this one, the force of attraction is going to be equal and opposite, and that force of attraction is going to be 4 times bigger than this force of attraction because there's 4 times as much charge here. And if we added 4 times here and 4 times here, the force would grow by 16 times. And so when we hang these 2 charges, they push each other apart, but at a much steeper angle than these. And the reason they're at the same level is because the force is equal and opposite. The only thing that would make them not at the same level, this will come up in the assignment, is if the mass of one of these 2 balls is bigger. So if the mass of this were bigger, it wouldn't be at as high an angle. But for this exercise, we're considering all the objects to be identical. Okay, that brings us to the next to last part of this very long lecture. Pause the video. So finally, we need a way to be able to calculate the exact magnitude of this force, and for that we have Coulomb's law. And we know about the attraction and the repulsion, and if you think about it, what's going to determine the strength of that attraction and repulsion? Well, we already discussed that. We discussed that more charge on either charge or both charges will increase the force in proportion to how much you increase the charge. In other words, double one charge and the force will double. Double the other charge and the force will be 4 times bigger. We also discussed in the polarization example that the force depends on distance, but we didn't discuss how. So there's this r squared, and that means the distance between the centers of the charge. If they're not truly points, you measure from center to center, and that distance will determine the force inversely proportional to the square. Notice how I said that, inversely proportional to the square. So if you recall, the force of gravity last semester operated the same way. It was an inverse square relationship. We'll talk more about this in the future. But what it means is if these two charges are 10 centimeters apart and I move one of them, so now they're 20 centimeters apart, the force will be 4 times weaker. If I move it towards here, so it's 10 times closer, the force will be 100 times greater. It's an inverse square law. So this is the equation we use. And what is K? So what is K? K is the proportionality constant. K is the constant in the equation that allows us to get the force in newtons given the two charges in coulombs and the distance in meters. So let me write down what K is. So once again, K is the proportionality constant. Actually, it's often written this way, 1 over 4 pi epsilon naught. What is epsilon naught? Epsilon naught is a fundamental electrostatic constant in nature. It is more fundamental than K. And just like pi is a natural mathematical quantity, or E, epsilon naught is the fundamental electrostatic quantity. Correctly, it should be written as 4 pi epsilon naught. A lot of textbooks do that. But this is a lot to write. So we often just simplify it by this convenience constant, K. So K is a convenience constant and a shorthand way of writing this. This is the value of it. It's so close to 9.0 that in most cases you can just use 9.0 to do the calculation. And notice the units, newtons meters squared per coulomb squared. When you put K into this equation, the units will come out in newtons. Okay, finally getting near the end. Here's 2 situations. 3 charges in a line and 3 charges arranged in an equilateral triangle. 2 separate situations. Let's find, now this charge here is attracted to these 2 charges. So if we focused on this charge, we would have 2 vectors of different lengths in the direction of these 2 charges, and the net force on this charge would be the sum of those 2 vectors. If we focus on this charge, there would be a vector of attraction in this direction and a vector of repulsion in this direction, and those 2 vectors would add. So in problems, you will be asked to find the force on any one charge in given situations, and so you should draw a vector diagram and then use your knowledge of vector addition to solve the problem. So in this case, let's find the force on, we have a positive charge of 1, a negative charge of 2, and a positive charge of 3, all separated by a distance, let's say it's d. Same thing here, d. They're all separated by the same amount. And so draw the vectors that show the forces acting on charge 3, which we might call Q3, like in the problems. We give them names, Q. And in this situation, draw the vectors acting on this charge and think about how you would add those vectors using vector addition methods. So draw the free body, quote-unquote, free body diagram of this charge in this situation and this charge, and then come back. Okay, so the first situation, there's two vectors. This is a 2 and a 3, so I'm drawing that a certain length. I'll think of that as a 6, 2 times 3, right? And just think of the distance as 1. So this is 6 units long. That's the force of this charge repelling this charge. Now this charge acting on Q3, or the third charge, is attracting, and it's a 1 and a 3, so that's 3. So you might think it's, oh, it's half of this. This is a 6, this is a 3. But no, it's twice as far away, and when you square that, that's 4. So this is actually 8 times weaker than this. If this is 6 units, this would be whatever, it would be 6/8, or 3/4 of a unit long. Now, to add these two vectors, just use Coulomb's law and call this positive and call this negative, and then you're done. And if you use the IJK notation, you may need to review that. I is a vector in this direction, J is a vector, a unit vector in this direction, and K is a vector along the z-axis coming in and out of the page. We will use that notation, so we can review that in another time. This answer is going to be a positive vector along the x-axis. When we come to this situation, it's a lot more complicated. So here's a 1 and a 3. This has a magnitude 3, and so that's attraction. And so that, let's call that 3 units. In this case, the distance is the same, right? Because it's the two charges and the distance between them. You have to step through it piece by piece. There's a force due to this interaction, and then there's the force due to this interaction. In this case, this is twice as big. But in order to add this, you're going to have to use vector methods to find the x and the y component of each vector, and then add those. You can see that the two x components are in the same direction, but the y components are in opposite directions, and then you have to take those components and add them, and then you have to reconstruct the vector. So if we need to review vector addition and subtraction, you should talk to me or a tutor, or maybe I should post the vector video from last semester. Hopefully most of you remember this. So most of the assignment is doing problems such as these for a variety of different situations. And the last thing, the superposition principle, just says that if you have two force vectors, the result is just the superposition or the addition of those two vectors. There's no, when you introduce a second charge, that introduces another vector. It has no effect on this vector. That's the idea of superposition. So if we have this one, these two charges, this is the vector. If I bring in a third charge, we have another vector, but this vector is not affected by the presence of this charge. So the superposition principle in its shortest form is just add all the vectors as vectors using normal vector addition methods. Okay, I think we're done. Good luck with assignment 1. Get in touch with me, use the tutors, and get a good head start on assignment 1.